Then I would like to talk something about confirmation time by adding what's called a finality layer, which we are the first blockchain to solve. And therefore, I mean, the next 15 minutes or so are going to be with some visible pride. I mean, here we have a really nice feature. And what this thing is about is how fast can you trust the transaction that you put on the blockchain? And just to see why there would at all be a problem with that, we have to dive much more into how this lottery thing is actually helping us agree on what the transactions are. Okay, so remember, the way a blockchain works is somewhere in the world, someone wins the lottery and gets to send out what's called the next block. So a block is just something where, I mean, there are some transactions in it, and then there is a certificate proving that the one that built the block actually had the right to build this block. So when we have a new winner over here, what this party there will do, what that node will do, is send out a new transaction saying first green, then red. Here's my proof that I won the lottery. And then it points back here to what it considers the previous block. And that's just to order all the transactions in the system. So it now means that if you are looking at what are the transactions in the system here, it would be 1, 2, 3, 4. Okay. So you just point, where am I adding these transactions here? That's very nice. These things are called blocks. The pointers then makes it a chain, and now we have a blockchain. Okay. That's really cool. We would be done if it would just remain a blockchain. But the problem is, unfortunate things can happen. For example, the lottery is completely distributed. People are just sitting locally and seeing if they won. So sometimes it happens that two nodes win the lottery at the same time. Okay? And then they send out, both of them, a new block, and then it will look like this. The one builds there and the other one builds there. They don't have time to see each other's block before they extend the chain. So now it's not a blockchain, but a block tree. That's unfortunate, because we would like to have one truth. I mean, what's the order of transactions now? Is it 1, 2, 3, 4, 5, 6, or is it 1, 2, 3, 4, 5, 6? I mean, the idea in Bitcoin was then to say, I mean, we resolve this by just relying on luck. The rule is when you win and get to extend the chain, you have to extend what you consider the longest chain. And if you have two that's equally long, just the one you saw first, some kind of tie-breaking rule. So there will be some kind of forking going on because of this. But we have this general rule about extending the longest chain, which will resolve it. So at some point, someone wins and extends there. And now the rule is just, now this is the truth, okay? So it means if you ask, what are the transactions in the system, it would then be 5, 6, 7, 8, and this stuff never happened. Okay? So you just ignore it. That's of course annoying if this here was a transaction that where someone transferred you 100 million to buy a rare Lamborghini. You gave him the keys, he drove away, and now the payment is gone. Right? And up here he transferred it to another guy, so the account is empty. Okay. Maybe it doesn't happen too often, right? It gets worse than this. Another way it could happen is there could be some of the nodes in the system that's actually interested in this happening. Say the guy that paid you for the Lamborghini. So if he's controlling some of the nodes in the network, he can do this naughty thing that say he wins the next two nodes. If he controls 10% of the stake, this will happen with probability 1%, which is already bad enough. And then he could add both of them like this. So he extends on the shortest chain. So now the truth is, if someone would ask you what's the stake in this system here, it would be 5, 6, 7, 8, 9, 10. And this stuff never happened. Okay? But he can keep doing this. So if there's a lot of corrupted parties in the system, next time they could add it here. And then if it wins two more, it could add them here. So you could get longer and longer, stuff that you thought was the truth that just disappears under you. Money you thought you had, stuff that already went up to higher level applications that just appear under you. And it's more or less impossible to code anything on top of this. And even if you think most of the time it doesn't happen, if there's a chance it happens, and you want to build a high I mean, like a really critical application on top of it, you have to handle it. And that's kind of the worst case. You have to sit and program a lot of stuff for events that never happen, right? It's completely impossible to program on top of such a thing in a reasonable way. Okay. So forking also happens because of malicious behavior. And very simplified, one can show that, I mean, the possible rollback lengths, I mean, what's the longest chain that could suddenly disappear from my view of what is the truth, is proportional to something like how slow is the peer-to-peer network compared to how fast you produce blocks, times the fraction of corruption. And the reason why the slowness of the peer-to-peer network matters is, remember what was dangerous if you had two honest winners like here, that didn't have time to see each other's block, then they extend and create a tree. And that means you should create blocks much, much slower than you can propagate them. So you build in a chain and not on the same thing. So slow peer-to-peer networks are dangerous and corrupted parties are dangerous. And in particular, combination of them is very dangerous. So this gives us this problem of when do I trust a transaction? Let's say someone paid me here for my car, and I wonder when should I give him my keys, right? So if your blockchain is looking like this here, it's after a few blocks appeared. I say you look 2 blocks back and you say, nah, probably this one is good now. You give him his key and he drives away. But that could also be that we are in a high corruption, slow peer-to-peer network setting because, for example, the peer-to-peer network is being slowed down by a denial of service attack. And then the situation could be looking like this here instead. And this means, I mean, we have 2 competing chains, one here and one here. And it's not completely sure which one of these 2 is going to win in the end. That means if you're going to hand out the keys to your car, you better make sure that you're paid all the way down here. Now, if this here was Bitcoin, for example, and each block takes 10 minutes, you have to look far back. And as a cryptographer, with small probability, something we would typically say 2 to the minus 60. And if half of the network is controlled by an adversary, that means you should look at least 60 blocks back to be secure on Bitcoin. 60 times, well, that's something like 10 hours, right? It's a long time. It's a long time to stand there with the keys. It's even longer if you just bought some peanuts in a shop, right? So, and even, I mean, I would even say, even looking far enough back is never a solution because you never fully know whether you looked far enough back. And that means ultimately, if you're building a critical application, you need to handle that exceptional day where you get a rollback that was longer than you expected, or your whole thing would crash down, right? If you build your application like that and it's a critical application, there will be an investor that says, this line in the code here where it just says everything just crashes, what's that about, right? So it's not good enough. It's good enough for like a toy situation like that Bitcoin was meant for, but it's not good enough for building anything like real-life high-stake applications. So what can we do about it? So it looks like if we pick, some cutoff point and say, you know what, I look this far back, and I consider everything that's behind this point here, I consider that safe, right? Then sometimes, in this case here, it could actually fail because one of these here is eventually going to disappear, right? I could also choose to look very, very, very far back. And then it would take a month for stuff to be final in my world, right? And then probably it never happens that you get a rollback that long. But in this kind of Nakamoto Style Consensus, you need to pick one of these. Either you look very, very far back, and it's very slow to get a transaction considered final, or you look back very short, like 6 blocks or something silly, right? And then you run a real risk that someday you'll get a rollback that long. But you have to pick, right? So you have to pick either fast finality or high assurance. There's no way to get both of them. You need to look some number of blocks back. Now, a recurrent design principle we have is whenever the world imposes on you to pick between 2 things, like either fast finality or high assurance, and it looks like you cannot have both, we will say, I'll take both, thank you. Okay, so let's try to now make a design where we get both of them, okay? We'll want to have fast finality and high assurance. Okay, how do we do that? The way we do it, ignore the code. But the way we do it is we're going to run a fairly simple procedure which we call finality. Let me do it in pictures instead. So the way it works is we're going to have, for the blockchain, since the last was going to be a finalized block, let's say the last one was down here, there will be a deterministically picked committee, or rather, it's a committee everyone knows who is. And they're going to run a good old, what's called BFT consensus algorithm. This is stuff we have known since the 80s. This is the kind of stuff you did if you had like 3 databases running to have replication, and one of them crashed. You would like to know which one of them is the truth. Right? So what these algorithms would do is now and then the databases could run a BFT algorithm. Each of them report what is my view at the truth. And then you run an algorithm, and if they all agree, it will come out and say, check, you agree, and then you know what the state should be. And if there's a disagreement, it will come out and say, you disagree. This is an oversimplification. That's basically what it does. It checks whether you agree on a value. And you will all end up agreeing on whether you agreed or not. So what do they do? I mean, these will just be bakers that have this special role of being on the committee. So what they will do is they will pick some height. Let's say height 1000. It was just agreed that the next place to do finalization would be at height 1000 in the tree. So what they do is when they reach height 1001, when what they consider the best chain has length 1001, they will look one block back and then vote on what they see. So that means, for example, if they are sitting like this here, I mean, this guy would vote for that, this one will vote for that, this one for that. So they're voting for 2 different values, so the algorithm would fail, and they'll all learn you don't look at the same thing when you look one back. Then they do it at height 2. So they try to finalize the same height, 1000. Now they just wait until they're at height 1002. They look 2 back and vote for what they're seeing. Again, they disagree on what they're looking at. And then they do what's called a binary search. Now they do it at height 4, 8, 16, 32, and so on. And already at height 4, we see that if they look 1, 2, 3, 4 back, they all see the same value. So the BFT algorithm is going to come out with, you agree on what you're looking at. So now since they all agree on what they're looking at, they know what they agree on, and that is now considered a final node. They'll all sign off on that. Everyone knows who the committee is. So they will get all these signatures and see, oh, the committee is signing off of this thing. So it's now, by every baker in the network, considered a final node. And then, bam, you just scratch everything that's not behind it. So everything that's behind the final node is considered final. And everything that branched off it will just be erased. Okay? And that means that could be a bad thing. I mean, if my car was paid here, that's annoying. But at least I knew that it was not final yet. That's the important thing here. You know when something can disappear, maybe, and when it can't. And you know now exactly, if you were paid here, you can now hand over the keys to your car, and the money will never go away, because it's just by algorithm illegal to ever roll back behind this thing. This is just defined to be final. And that's what gives you finality. Okay? Now you know that this part of the tree will never disappear. I mean, non-final stuff, you can still use it if you're buying peanuts or swiping money to a friend that you know where you can swipe them again by. But if you're really handing over the keys to your Lamborghini to a guy that doesn't tell you what his name is and wearing a mask, you wait for it to be final. So that's what it's giving you. You can do high-risk applications in this kind of thing. What's really cool about this now is you're getting both of them now, right? You have like, with finalization will happen in best case, right? So most of the time there is not really a lot of branching. So already when something is like 2 or 3 blocks deep, and right now on the testnet it's typically just 1 deep, it will finalize, right? So that means within 1 block you know it can never go away again. Whereas if you're doing an ad hoc thing, you would have to wait like 60 blocks and still run a risk that it might go away again. So in that case, you have a worst case, waiting time for finalization, right? So this gives you a better guarantee and is faster. right? So it was not true that we had to choose between either, fast finalization or high assurance, right? No, we'll take both. Thank you.